In this lesson, we embark on a detailed exploration of the Verisense network architecture, focusing on its critical elements: validators, monitoring, and nucleus. Previously, we introduced the foundational idea of Verisense as an active blockchain. Today, we will unravel the sophisticated structure that brings this innovative concept to life. We will carefully analyze each layer and examine the three fundamental components of the network. We begin with the validators, who form the core of the network's security. Next, we explore the Monadring Subnets, which ensure scalable consensus. Finally, we delve into the Nucleus Execution Environments, where autonomous on-chain agents are activated. Understanding the roles and interactions of these components is crucial for comprehending how Verisense establishes a new and robust framework for executing and coordinating on-chain agents. Part 1 of our discussion introduces the Verisense layered architecture, marking a paradigm shift in blockchain technology. To understand the groundbreaking nature of Verisense, we first need to reflect on the limitations inherent in the blockchain platforms it aims to replace. Traditional blockchain architectures are inherently passive, as their state can only change when an external transaction occurs. Despite their computational abilities, smart contracts within this framework function as dormant engines, unable to initiate actions autonomously. They require an external call, whether from a user's wallet or an off-chain oracle, to become active. This passivity poses a significant limitation, restricting their ability to act as fully autonomous agents, capable of responding proactively to the passage of time or changes in external conditions. Verisense tackles these limitations by introducing the concept of the active blockchain, which represents a fundamental shift in blockchain design. An active blockchain expands the traditional state machine model to naturally support proactive on-chain execution. This is represented as an extended state machine, where the event set E includes both external transactions and two new types of internally generated events: asynchronous external call events and timer-triggered events. This expansion allows on-chain modules, which we will soon introduce as nuclei, to act independently. They can autonomously fetch data from external APIs, invoke services on other servers, or perform tasks following a set schedule, all without needing an external trigger or transaction. The principle of native proactive input-output is the core innovation driving on-chain autonomy, and it serves as the cornerstone of the Verisense architecture. To fully grasp the potential of the active blockchain paradigm, consider its sophisticated and hierarchical architecture, meticulously crafted for security, scalability, and functionality. This innovative design rests on three vital and interconnected components: validators, monitoring subnets, and Nucleus Execution Environments. Initially, we have the validators. They form the foundational layer of the network, ensuring global security, integrity, and governance. Next are the monitoring subnets, which are lightweight and independent consensus groups that are partitioned from the main validator set. These subnets are specifically designed to create scalable and parallel execution environments. Lastly, the Nucleus Execution Environments are specialized runtimes hosted within the monitoring subnets, providing an on-chain home for deploying and executing proactive agent logic. The architecture's diagram presents a clear picture of this hierarchical structure. At the top is the global pool of Verisense validators. These validators are selected through a verifiable random function, VRF, a cryptographic method that guarantees fairness, unpredictability, and decentralization in participation. This global group is then divided into smaller, specialized groups known as monaderings. Each monitoring operates as a distinct and autonomous consensus group. For example, the diagram details monitoring 1 running Nucleus 1 and Nucleus 2, whereas monitoring N operates Nucleus 4 and Nucleus 5. Within each nucleus, the environment is tailored to execute an application's or agent's code. This layered design reflects Verisense's strategic response to the classic blockchain trilemma of security, scalability, and decentralization. Rather than optimizing all three aspects in a single, monolithic layer, which is often deemed impossible, Verisense assigns distinct responsibilities. The global validator set upholds the network's overarching security and decentralization, representing its staked value and integrity. Simultaneously, the Monadring Subnets facilitate scalability by enabling applications to operate in parallel on smaller, dedicated consensus groups. This approach avoids performance bottlenecks typical in monolithic chains, where a single active application can impair performance for all users. This strategic separation of concerns is a hallmark of modern blockchain design and is fundamental to Verisense's ability to support complex, high-throughput decentralized applications. Let us first explore verifiable random functions. At the heart of Verisense's scalable subnet architecture is Monadring, a consensus engine that empowers independent groups. Monadring is a lightweight consensus mechanism inspired by the classic token ring networks from the early days of computing. In this approach, a designated subset of Verisense validators forms a logical ring through which a unique cryptographic token circulates sequentially from one validator to another. According to the protocol, only the node in possession of this token holds the authority to propose the next block of transactions and commit state modifications. This rotating leadership drastically simplifies the consensus process by eliminating the resource-intensive competition and complicated messaging overhead that is typical in many proof-of-work or proof-of-stake systems, where all nodes compete for leadership simultaneously. The monitoring architecture is visualized in a diagram that outlines the lifecycle and security features of a Verisense subnet. The process is broken down into several key stages. Initially, nodes go through an initialization and topology formation phase. Here, they become initialized nodes, undergoing a SAP phase that involves VRF and key sharing. A verifiable random function ensures a fair and unpredictable ordering of the nodes, while threshold key sharing establishes a collective security model. This phase results in the formation of the logical ring structure known as the monitoring topology. Next, consensus is achieved through a process termed consensus through token circulation. This involves token circulation, where a unique token is passed from one node to the next around the ring. The node with the token is granted the exclusive authority to propose and commit state updates for that particular turn. To enhance privacy, the protocol employs fully homomorphic encryption, FHE, mitigating strategic manipulation. By cryptographically transforming the consensus process from a perfect information game into an imperfect information game, FHE conceals sensitive data, thus preventing validators from acting on privileged information, such as front-running transactions. The mechanism is designed with robustness and fault tolerance in mind. It is resilient to failures and malicious actors. A malicious node can be addressed through fault tolerance measures, including voting by other nodes and slashing the malicious node's staked assets. Node rotation also helps maintain network health and security. Finally, the process incorporates dynamic membership. The subnet is flexible, allowing nodes to join or leave the ring without disrupting the consensus process. The security and integrity of the subnet during these changes are maintained through a key resharing procedure, which securely updates the group's cryptographic keys. A token passing workflow, as detailed in the Verisense white paper, operates with a remarkable level of simplicity and efficiency. Let's examine the process for each node within the ring. Initially, a node receives a token that contains the current confirmed state of the subnet, along with a list of pending events proposed by earlier nodes in the ongoing cycle. The node's first task is to validate and execute all the events in the token's event list by applying these state transitions to its local state replica, thus reaching an updated state. Subsequently, the node collects any new local events it has generated or received during its operational period. These new events are appended to the token, and the token's state field is updated to reflect the state after incorporating the node's contributions. To conclude its role in the process, the node applies a digital signature to the token. This action provides a cryptographic affirmation of the new state and associated events. The node then forwards the signed token to the subsequent validator in the ring. This token passing cycle persists within the ring, achieving a fully committed batch of events in the subnet's local ledger only after the token completes a full rotation and receives validation from a pre-specified quorum, such as a majority of the subnet's nodes. This method ensures that the subnet maintains a universally recognized and ordered sequence of events, reaching consensus with minimal computational and network requirements. To ensure robustness, the Monadring protocol has been fortified with a combination of advanced cryptographic techniques. These enhancements serve to maintain fairness in participation, ensure data privacy, and secure the collective actions of the protocol, turning a basic token ring into a powerful and reliable consensus mechanism. Firstly, we examine the role of verifiable random functions. These functions introduce fairness and unpredictability by employing verifiable cryptography to randomly determine which participant assumes the leader role, thereby eliminating the possibility of manipulating the sequence of turns. Next, let's consider the use of fully homomorphic encryption. This technique ensures privacy and confidentiality by encrypting sensitive data within the token. As a result, state transitions can be verified without exposing confidential information to the nodes that process the token. Lastly, threshold signatures are integral for securing collective actions. They necessitate a quorum of validators to approve critical activities, such as state root updates or external transactions, thereby safeguarding against unilateral control or fraudulent actions. Firstly, let's delve into the concept of verifiable random functions, VRFs, as employed by Monadring. This technology is crucial to maintain fairness and thwart any adversarial efforts to manipulate the leadership sequence. In essence, a VRF is a cryptographic tool that enables a party to produce a random output along with proof of its correct generation. Within Monadring, VRFs randomly decide the arrangement of nodes in the logical ring or choose the initial token holder for each consensus cycle. This ensures that the leadership sequence is unpredictable, making it impossible for an adversary to foresee when they might control the token. This unpredictability effectively neutralizes attacks that rely on placing a malicious node in a strategic position to disrupt or censor crucial transactions. Next, in terms of privacy protection on the blockchain, Monadring integrates fully homomorphic encryption, FHE. FHE is a groundbreaking encryption method, allowing computations on encrypted data to yield encrypted results that match operations performed on unencrypted data. In Monadring, this means that sensitive data within the token remains encrypted during its circulation. Nodes can still execute necessary updates and checks on this data without accessing the underlying confidential information. This provides a strong defense against information leakage and strategic misuse, particularly in small, participant-sparse subnets, where a node might otherwise exploit sensitive data from the token content for an unfair advantage. For the realm of collective decision-making and action security within the subnet, Monadring employs a threshold signature scheme. Initially, during the subnet setup, validators undergo a distributed key generation process, producing a collective public key while the private key is divided into numerous shares, with each validator possessing only one. This structure ensures that no single entity controls the entire private key. When the subnet needs to perform a critical action, like signing the state root for the main chain or authorizing transactions on an external blockchain, a quorum of validators, e.g. 2/3, must collaborate by combining their private key shares to produce a legitimate signature. This mechanism ensures that no single malicious actor or colluding group can falsify group decisions or unilaterally manage subnet assets. The system also supports secure key resharing, allowing validator changes over time without compromising shared key security. Combining these three cryptographic technologies, VRF, FHE, and threshold signatures, establishes a solid game-theoretic model that provides more than just layered security. The white paper likens this to a one-shot prisoner's dilemma, where in environments with minimal participants, the threat of collusion and strategic attacks increases. The Monadring design mitigates these threats by systematically removing any incentives for dishonest conduct. The unpredictability of VRF precludes attack planning, FHE prevents informational exploitation, and threshold signatures ensure that no lone actor can unilaterally inflict harm. Ultimately, rational actors find that adhering to protocol rules honestly is the most logical and rewarding strategy. vital for the integrity and sustainability of Verisense's architecture upon which these specialized subnets depend. To begin with, let's discuss the resilience built into distributed systems for handling failures. A distributed system is only as strong as its ability to manage faults effectively. Monadring integrates robust fault tolerance mechanisms to ensure the network's liveness and safety, even when some nodes are offline or acting maliciously. The sequential nature of the token passing protocol presents a potential risk. If a node holding the token goes offline, it could halt the entire subnet. To counter this, the protocol uses a timeout feature. If a node fails to produce a valid update and pass the token within a predefined timeframe, the other nodes in the subnet initiate a timeout, effectively bypassing the stalled node and handing control to the next validator. This mechanism ensures that the network remains live and progresses smoothly. In instances of malicious behavior, such as when a node proposes an invalid state transition, the protocol's defenses are equally resilient. As validators receive the token, they conduct their own verification processes. If a malformed or unauthorized event is detected, they will reject the proposed update. The token can then be rolled back to its last known consistent state, discarding the malicious node's contribution, and thereby preserving the integrity of the subnet's ledger. For persistent or severe misbehavior, the honest majority of validators can reach a consensus to penalize the offending node by slashing its staked assets and permanently removing it from the subnet. This imposes a significant economic penalty on those acting against the network's interests. In the third part of our series, we focus on the concept of the nucleus, which serves as an on-chain home for agents within the Verisense architectural framework. To understand its role, consider the nucleus as the custom-built vehicle constructed around the high-performance engine known as Monadring. Essentially, a nucleus acts as the dedicated, sandboxed runtime environment where a developer's decentralized application or autonomous agent logic is deployed and executed. It's comparable to a mini blockchain crafted for a distinct purpose. Each nucleus is an instance of a Monadring subnet, meaning that it operates under its own set of dedicated Verisense validators. This setup ensures that the performance and state of one application are completely independent from others on the network, providing an isolated yet secure environment. Two key features define every nucleus, shaping its function and user experience. First, before deployment, all application logic is compiled into WebAssembly WASM bytecode. WASM serves as a portable binary instruction format that delivers high performance, security, and platform independence. This compatibility guarantees that the application code runs deterministically and identically across every validator node within the subnet, which is crucial for maintaining consensus. The second defining feature of the nucleus is the innovative reverse gas model implemented by Verisense. Unlike the traditional approach used by most public blockchains, where end users must pay transaction fees, or gas, for every on-chain action, the execution costs within a nucleus are covered by its publisher or developer. This mirrors the business model of modern Web 2 applications, where the service provider assumes the infrastructure costs. This method significantly lowers the entry barrier for users, facilitating seamless and seemingly free interactions. As a result, it promotes wider adoption and allows for the creation of more complex application designs that are not limited by user transaction fees. First, let's explore how to achieve proactivity within a deterministic framework. This represents one of the most groundbreaking and technically challenging aspects of the nucleus. The promise of the active blockchain is that on-chain agents can interact with the off-chain world. However, this introduces a fundamental paradox. Blockchain consensus requires absolute determinism. Every node executing the same transaction log must reach the exact same final state. Meanwhile, interactions with the external world are inherently non-deterministic. For instance, an HTTP API call might return different data at different times. Response times can fluctuate, and the internal clocks of different validator nodes are never perfectly synchronized. Therefore, the central question is how a nucleus can make an HTTP request or respond to a timer without breaching the deterministic requirement of consensus. Verisense addresses this challenge through an elegant two-step event mechanism that serializes non-determinism and safely integrates it into the consensus process. Consider the scenario where a nucleus needs to fetch data from an external web API. To begin, when the nucleus's WASM logic decides that an HTTP request is needed, this intention is logged as a deterministic event and placed into the Monadring token. As the token circulates, it arrives at the current leader, the token holder. This node exclusively reads the request event and performs the actual, non-deterministic HTTP call to the external server. Upon receiving the response from the server, the leader node packages the result, complete with cryptographic evidence of its authenticity, like a TLS proof, into a new response event. This new event is then added to the token. The token, now containing the canonical result of the external call, continues its circulation. Other nodes that receive it see the response event. They do not make the external call themselves. Instead, they process the result provided by the leader deterministically, which has now become an immutable part of the event log. The same principle of the leader executes, others verify, applies to timers as well. When a timer is set, it is logged as an event. Once the time elapses, the first node to notice this, typically the current leader, generates a timer-fired event and injects it into the token. All other nodes then process this event deterministically. Through this mechanism, the on-chain and off-chain worlds are seamlessly interconnected, allowing nuclei to be active and responsive while maintaining the perfect, verifiable consensus necessary for a secure blockchain. It is essential to recognize that this advanced proactivity is not an isolated feature of the nucleus. Instead, it is an emergent property resulting from the entire Verisense architecture functioning in harmony. The rotating leader mechanism of the Monadring provides the necessary serialization, securely isolating the non-deterministic external action to a single node. The two-step event protocol is the specific process that allows the outcome of that action to be reincorporated into the consensus process in a fully deterministic way. Lastly, the main Verisense validator network serves as the ultimate layer of security and accountability, as the state roots generated from these proactive events are periodically signed by the subnet's threshold key and securely anchored on the main chain. It is the seamless integration and interaction of all three architectural layers that convert Verisense into a genuinely active blockchain. In conclusion, the Verisense architecture exemplifies excellence in structured design, meticulously crafted to address the limitations of passive blockchains and usher in a new era of autonomous on-chain applications. It effectively differentiates various concerns to tackle the blockchain trilemma, offering a platform that simultaneously achieves security, scalability, and decentralization. At its core, the global network of Verisense validators ensures comprehensive security and trust across the ecosystem, with participation managed through a method of cryptographic selection that is both fair and unpredictable. This strong foundational layer supports the development of high-performance, application-specific subnets. These subnets operate using the Monadring Consensus Protocol, which is a lightweight, efficient, and secure token ring mechanism fortified by advanced cryptographic tools such as verifiable random functions, VRFs, fully homomorphic encryption, FHE, and threshold signatures. Within these secure and scalable subnets are the nuclei, which serve as proactive execution environments where decentralized agents operate. Through a novel two-step event mechanism, the nuclei are capable of safely and deterministically interacting with the off-chain world. They handle timers and retrieve external data while maintaining seamless consensus among their validators. This structure forms the basis for the future development of decentralized AI, intricate financial agents, and genuinely autonomous on-chain systems. Thanks for watching.